For calibration of probability model?
Not probability model, just for the actually for the calibration of the logic model.
Oh, okay. Thank you.
Yeah. The probability model, the one I should say that the materials covered about the probability model is something it's better for you to know, but it's not necessary for you to apply them in the final exam, or especially for the calibration method. Just give you an idea about how it's calibrated, and you don't need to really work on that. Okay, I'm gonna share my screen. Okay, are you able to see my screen now?
Yes, Professor.
Okay, just let me just see what happens, why it always not showing. I'm gonna exit the sharing and then do it again. It happens. Okay, sharing. And okay, it's working. So last week we have introduced the multinomial probability model, and this one assumes that the random term follows a normal distribution, a multivariate normal distribution, and also it does not assume that those random terms are independent to each other. So it's more flexible compared with the multinomial logic model. That's also the reason for us to introduce this new method. So just a moment, what happens? Just a moment. Okay. So we have a moment, just a moment. It looks like it always has some rotation issue. Okay, so in the lecture today, we're going to focus on the calibration method for the probability model. It's much more complicated compared with the logic model. So that's the reason I just request you to know how it's what's the steps to do this calibration, but it's not necessary for you to know. If we in the future, if you need to do any research about the calibration of the probability model, you can go back to check the those kind of notes and explore some textbook, especially the textbook that I shared with you at the beginning of this class. So for the calibration of the multinomial probability model, we first need to specify what's the probability of choosing a mode K from the set of the alternatives. And in the based on the probability model, if we can define that the probability of choosing the mode K is as in a function of mj minus 1 and sigma j minus 1, which would be the mean and standard deviation of the normal distribution, and this one is related to the random terms that we defined for each alternative. So regarding to the probability phi here, it actually represents the probability of the variable maximization of zj. This zj actually shows the difference between the utility of one alternative to the specific utility of alternative k. And we want to make sure that the maximum value of zj is smaller than 0. And here we have the definitions about zj. Zj is actually the difference between the utility of alternative j and the utility of k. K is the one is the alternative that we're gonna select. We can actually specify new index j prime to make sure that all the index are continuous in the future analysis. So with that, we have the vectors for z, and that's z1, z2 until we get zj minus 1. Those vectors represent the difference from the first alternative to the jth alternative, except the case 1, which would be the one that we have select. And the zj tilde is actually defined as the maximization of all these j minus 1 z's. As we know that for this probability, we want to find out what's the maximum value of this difference, zj, and we have to make sure that zj is smaller than the maximization is smaller than 0, and which would be the zj minus 1 tilde is smaller than 0. And in order to find out what's the distributions of zj minus 1 tilde, we have to record the cluster approximation. And based on the cluster approximation, we actually showed this one in the previous lecture. The zj minus 1 is also a normal distribution with the mean of mj minus j minus 1 tilde and the standard deviation of sigma j minus 1 tilde. So this would be the distribution we defined from one approximation. And also we know that for the for no matter the multivariate logic model or the problem model, we assume that the utility function consists of two terms. One is the deterministic term, the other one is the random term. For the deterministic term, we assume that it follows a linear function of the attributes. So the vi as a function of xi, and we have some specific settings about the coefficient theta, which would be the parameters we have to calibrate. So that's the deterministic term. And we also have the random term for each alternative. So for the first alternative, model 1, it's v1 plus epsilon 1. Epsilon 1 is the random term. And in this case, we have j different alternatives. So we have a set of j different random terms. And they actually follows the multivariate normal distribution. And in this equation, in this matrix format, the deterministic term is the linear function of the attributes. And from the probability model, we assume that the random term follows the multivariate normal distribution with the mean value of 0 and the standard deviation of sigma epsilon. So that's what we set for the random terms. And we have to just a moment. I have no idea what happens about my computer. Let me just try to use this. So for the matrix of the standard deviation, it's actually the which would be the covariance matrix. We have J by J matrix, and this J by J matrix is something we don't know, and it's also the parameters we have to calibrate for the probability model. And now we have all the definitions about the utility function. With that, we can then go to the definition about the matrix format of the z values. So z actually equals to actually zk equals to uk plus 1 minus uk. You can find out the definitions about the other z values, and it will be also be very intuitive for you to find out the difference about the deterministic component and difference of the random components. And this one, apparently this one is very complicated, and it will not be easy for you to do an analysis. So what we do is like we will try to apply the transformation matrix to identify the relationship between the z vector and the utility vector u vector. So this is the format of the transformation matrix. So basically, you have the -1 for the entire row, entire case row, and this is actually J by J matrix. So entire case row, and then you have the diagonal set as 1 for the other. No, it's a J by J minus 1 matrix. So that's what we get for the transformation matrix, and then obviously you can write them into the matrix format, and we assume that the transformation matrix is the delta. With that, we can then find out the matrix format for the deterministic component. So that will be V times the which will be V times the delta. And this one shows the V times delta shows the estimated utility for each mode. And similarly, you can find out the you can actually find out the you can actually find out the relationship between the error terms and for the z vector. And we were also able to find out the as for the z vector, z actually equal to, it's not easy to write it down. What happens? Z actually equals to u times delta, and that equals to v times delta plus epsilon times delta. So the random term is epsilon times delta. The deterministic term does not affect the covariance matrix of Z. So the covariance matrix of Z is actually determined by epsilon times delta. But we actually have already made some analysis about how to calculate the covariance of a random vector. If we know the transformation matrix and the original covariance matrix, you can easily find out the covariance matrix of Z as delta prime times epsilon sigma times delta. So that is the entire format for the covariance matrix of Z, and it actually be in the J minus 1 by J minus 1 matrix. We assume that the covariance matrix of Z is a sigma 1 square, sigma 1 2, sigma 1 I until you get the sigma 1 J minus 1. You can also find out the definition of the assume a set of values for the other rows. And with that, you can also assume that the find out the mean values. Say that Z, which would be the Z bar, that is determined by the deterministic component. As we know that for the random term epsilon, it follows the normal distribution with the mean of 0 and the covariance matrix of sigma Z, and this indicates that the epsilon times delta will also have the mean of 0. So what we get for the Z with the mean of Z1 prime, Z2 prime, which is only determined by the deterministic term. And now the next thing we need to do is like we have know the mean of the Z. We have already know the standard deviation of Z. What we need to get is find out what's the distributions of the maximum Z. With that, we have to record the Clark's approximation. Assuming that the omega I is the maximum of two variables, omega I minus 1 and omega I, And we also define that the omega I minus 1 tilde is the maximization of omega 1 to omega I minus 1. And you can which just means that it is the maximum value of omega 1, omega 2 until go to the omega I. And with this kind of iteration, we can then find out the distributions of the omega j minus 1. So to conduct the Clark's approximation, we first assume that omega I follows a normal distribution with the mean of mi tilde and the variance of the sigma I tilde. And mi tilde is determined by the mean of the covariance, the mean of the random variable omega I, and also the mean of the omega I minus 1 tilde, as well as for the sigma I tilde. It can also be determined by the properties of the omega I tilde minus 1 tilde and omega I. And so that's what the Clark's approximation stated about the estimation of the maximization of two normal variables. If we start from the first one, z1 and z2, we can find out what's the distributions of z1, z2 tilde as the maximum value of these two, z1 and z2. With that, we can find out the mean and variance for z2 tilde. And similarly, we can extend this one for z3 tilde, which will be the maximum value of z1, z2, and z3. But we know that the maximum value of z1 and z2 will be z2 tilde. And we already know the distribution. So with the Clark's approximation, we can find out the mean values of the z3 tilde. We can find out the variance and also the covariance between the z3 and the z4, which will be applied for the next iteration. And we can, or with that, as we have already obtained the distributions of z2 tilde. You can then apply your estimated equations m2 tilde, sigma 2 tilde, sigma 2 3 tilde, and so on. Apply all of them to this equation, and that will give you a full expression about what's the how to calculate the m3 tilde, sigma 3 tilde square, and the sigma 3 4 tilde, and so on. And this iteration will be repeated again and again. For eventually, you're gonna find out the distributions of the omega I tilde and even omega j minus 1 tilde. For you to find out the maximum value of j minus 1 random variables, that would be the z maximum value of z. So to do the calibration, we have to rely on all the calculations we mentioned previously. So for now, we know the formulas for the probability to choose the alternative k, and it actually follows the normal distribution with the mean of mj minus 1 tilde and the variance of sigma j minus 1 n tilde. And also there are in order to calculate this probability, you need to find out what's the value of theta, what's the value of the covariance matrix for the epsilon values. So this would be two unknown variables we have to calibrate. Assuming that you have p different attributes, with that you will have p plus 1 coefficients to calibrate. And for the covariance matrix, you actually have j times j plus 1 divided by 2 unknown variables to calibrate. To put them together, you totally have p plus 1 plus j times j plus 1 divided by 2 unknown variables or parameters to calibrate for the probability model. And again, we can rely on the likelihood function likelihood function to find out to do the calibration. For the definition of the likelihood function is the same to what we do for the multinomial logic model. And we are trying to find out the likelihood defined as the products of the probability for all the modes and all the observations. And here in order to do the calibration, we want to maximize the likelihood function. However, the issue here, the difficulty here is like it's different from the logic model. It has a closed form equations. For the probability model, as f follows the normal distribution, it's usually not easy for us to do the differentiation for the f function. So with that, it's not easy for us to derive the closed form format about the this maximization problem, and then it will be very hard for us to conduct the calibration. So, but still, we want to do the calibration. In order to do that, we're gonna rely on the heuristic method or some other numerical searching methods. So here we have some typical steps for the heuristic calibration method. First of all, we have to know what kind of input data we're going to have. We first need to know the number of the observations, how many individuals we have observed, and what's the mode we're going to take. And we also need to know the number of the alternatives that we will be available for the individual, and the parameters we have to calibrate, and what's the attribute for each parameter. So that's the input data we have to use. And for each parameter to do the calibration, say that we have p plus 1 theta values and j times j minus 1 divided by 2 coefficients or covariance elements. And for each parameter, we specify the minimum value and the maximum value as well as the initial guess. So in the calibration, we will just search all the possible values between the minimum and the maximum value, so that we will then find out which set of the parameters, theta and gamma ik, will be applied for us to maximize the likelihood function. So the core idea is very straightforward, but the computational complexity is very high. And regarding to the data set, we definitely know what's the attributes that we observe for each individual. That will be the xin for each mode. And then once we have all these things, we need to specify the format of the v, the deterministic functions, v is the linear function of the attributes xi, and we also assumed the covariance matrix for epsilon. You can actually try to specify the covariance matrix based on the problem described, so that you can reduce the potential number of the unknown variables you have to estimate. I'm going to show you one example in the next few slides about how we're going to specify v and epsilon. And now let's see one example about the how to do the calibration of the probability model. Here we will have the 3 different modes: the bus, trolley, and auto traveling in the city, and it's available for multiple individuals to take. And then we will apply the probability model. We want to calibrate the probability model based on the observations. And to specify the model, we assume that the deterministic component is a linear function of the travel time and the cost. So v is the function of travel time, ti, and the cost, ci. So vi equal to theta 1 times ti plus theta 2 times ci. And we also assume that the bus and trolley share the neglected attributes, and that won't affect the performance of the auto, which means that the bus and trolley are correlated with each other, but they are independent to the auto. So with that we can assume that for the for the bus and trolley, they are independent to auto. So we set the covariance matrix, set these four cells as 0 to represent the independence. And we know that the bus and trolley are correlated with each other, but we don't know what's the correlation. So we assume that the value is gamma. So now we will only have one parameter to estimate for the covariance matrix of epsilon, that is gamma. And then we can go to the calibration process. And for the covariance matrix of the epsilon, it should be in a valid covariance matrix, so that it must be in a positive definite. And that's the one required conditions for the covariance matrix. And with that we can say that if it's a positive definite, we have to make sure that the determinant of the matrix is positive, with that you get that for the gamma is actually the absolute value is smaller than 1, which means that gamma can be selected between -1 and 1. And now we need to specify what's the range of each parameter. So here we have two, if we go back to check the definition, we have two parameters, coefficient sigma 1 and sigma 2. We have one correlation gamma to estimate, so there are 3 variables to estimate. We need to specify the ranges of these 3 variables. For sigma 1 and sigma 2, you can say that the value varies from -100 to 1. This would be just some random variable we select. And for sigma 1, sigma 2, both say as the -100 to 1. And for gamma, we have specified the range is the absolute value should be smaller than 1. So we set the range from -0.99 to 0.99. And you can specify any initial values. Any values between this minimum and maximum value as the initial guess for the theta and gamma. And with that, you will be able to search all the possible values from the minimum to maximum, or apply some gradient methods to find out the optimal theta and gamma values efficiently. Once it's done, you will have the calibrated multinomial probability model. But I should tell you that this process is very complicated. The idea is very simple, but regarding to the computational cost, it's very computational intensive, and you need to rely on some computing softwares or some existing calibration package to conduct the calibration of the multinomial probability model. It's very time consuming. With that, I finished the introduction about a very brief introduction about the estimation method of the probability model. It's just giving an idea about how the calibration is conducted. It's not necessary for you to implement them for this class. It's not necessary for you to know how to implement them, how to use them for a specific example. But in the future, if you are interested about conducting any research related to probability model, just feel free to let me know. I can forward with you about more materials to read. Okay, so with that, I quickly finished the introduction about the calibration method of the probability model. Is there any questions about that before I jump to the tutorials about the Queen's OD? Okay. If there isn't any questions, I will go to the introduction of the Queen's OD tutorial. I may change to the other computer where I have the Queen's OD stored in the computer, and I'm gonna give you the introduction about how to do that. And before I start the tutorial, I hope has everyone downloaded the materials or at least download the compressed file for the Queen's OD. Okay. If there's any, I just assume that everyone has already get the software. So now I'm gonna start the introduction about the software, and let me stop sharing this computer and go to the other one. Probably I will stop recording this one and put them in two separate videos.